Hi everyone. In this video, I am going to tell you about Norton's theorem. Like Thevenin's theorem, Norton's theorem is also used when we are interested to find current in only a particular branch and when we don't care what rest of the circuit is. So in previous video, I have told you a brief outline what is a linear network. In this video, I am going to give you a more formal explanation of linear network. So what is a linear network? A network is said to be a linear network if and only if it satisfies two principles. The first principle is principle of superposition and the second principle is principle of homogeneity. To understand superposition principle, let's consider a network to which if xt excitation is applied, then it produces a yt response. Now suppose a particular x1t is applied to this network and it produces a response y1t, and if another excitation is applied to the network s2t, then it produces a response y2t. Now if this network follows superposition principle, then if both the excitations are applied simultaneously, then the combined response should be equal to y1t plus y2t. This is the general principle of superposition. So principle of superposition can be stated as total response due to multiple excitations or sources is equal to the algebraic sum of the responses caused by individual excitation or source acting one at a time. Now according to principle of homogeneity, if excitation to the network is multiplied by a constant alpha, then its response should also get multiplied by the same constant. This is the principle of homogeneity. That is, if excitation is multiplied by alpha, then response must also get multiplied by same alpha. This further implies if alpha is 0, then 0 input to the system should produce 0 output. If we plot a graph between response and excitation to understand this graphically, then 0 excitation should produce 0 response. So the relationship, whatever the relationship will be between the response and excitation, it will pass through origin. This means if response is equal to alpha xt plus c, then this does not follow the principle of homogeneity and hence the network is not a linear one. For network to be linear, this c must be equal to 0. So combining both the conditions mathematically, we can write alpha 1 x1t plus alpha 2 x2t must produce alpha 1 y1t plus alpha 2 y2t. So if any network follows this condition, then it will surely be a linear network. Now let's come to the statement of Norton's theorem. It says that across a pair of terminals, any linear network containing active and passive elements can be replaced by an equivalent network containing a current source IN, which is known as Norton's current source, and a resistance in parallel Rn, which is known as Norton's resistance. This means if the terminals are AV, then across these terminals we can replace this whole network. To make things clear, let's find current through this branch using Norton's theorem. This was the network, and to find Norton's short circuit current, we need to short terminals A and B and find this current. So now you can use either KVL and KCL, or you can use mesh analysis. Here I am using mesh analysis to find Norton's current. So for this network, Z matrix will be Z11 is 20, Z22 is 10, 5, 10 is 25, Z33 is 12, Z12 is -10, Z13 is 0, Z21 is -10, Z23 is also -10, Z32 is -10, and this is 0. So this is the Z matrix, and now we can write to understand this how I have done. You can check my video on mesh analysis. So this can be solved either by calculator or by Cramer's rule, and I3 will come out to be 2 by 7 ampere. So this current will be 2 by 7 ampere. To find Norton's resistance, the method is exactly same as that to find Thevenin's resistance. That is, we eliminate the voltage and current sources. We replace voltage source by conducting wire, that is, we short the voltage source and open the current source. So here there is only one voltage source, so after shorting that, the network will look like this. So across terminals A and B, resistance, Norton's resistance is equal to 10 is in parallel with 10, so this will be 5 in series with 5, which is combinedly in parallel with 10 and which is in series with 2 ohm resistance. So this comes out to be 7 ohm. After finding Norton's current and Norton's resistance, you can redraw the circuit like this. A current source IN and a resistance Rn in parallel, and these are the terminals A and terminal B. Now you can replace the 13 ohm resistance, and our aim was to find this current. Now this current, let it be I, can be found using current divider rule, which is Rn upon Rn plus 13 into In. So this is 7 upon 7 plus 13 into 2 by 7. 2 by 7 is In, this is In, and this is Rn, which is 7. Solving this, we get 1 by 10 ampere. So now let me give you a brief review of the method. We first need to find the short circuit current across the terminals, and then we have to find the Norton's resistance. To find short circuit current, we can use either KVL and KCL, or we can use mesh analysis. It's up to you. And the method to find Norton's resistance is exactly same as the method to find Thevenin's theorem. And for the detailed explanation, you can check my previous video on Thevenin's theorem. So this is how you replace any network with Norton's equivalent network. There is one more interesting thing that I want to tell you, and the interesting thing is the relation between Norton's equivalent network and Thevenin's equivalent network, and that is Norton's resistance is equal to Thevenin's resistance and Norton's current is equal to Thevenin's voltage divided by Thevenin's resistance. This is very interesting relation, and because of this relation, Norton's theorem is also known as dual of Thevenin's theorem, and this could be understood very easily. Just suppose if we draw the Thevenin's equivalent of the network taken in the example, then it will be like this. These are the terminals A and B, and you know Norton's current is defined as the short circuit current across terminal AB. So if we calculate the short circuit current here, this will come out to be VTH by RTH. This is RTH and this is VTH. So these relations are quite interesting because we can find Norton's equivalent from a Thevenin's equivalent, and vice versa is also true. We can find Thevenin's equivalent from Norton's equivalent using these relations. So this is all in this video. Thank you.